the elephants.
Welcome to today's webcast, Modular Open Systems and How the MOSA Approach is Helping OpenVPX Evolve, brought to you by Military and Aerospace Electronics Online. I'm Jamie Whitney, Associate Editor of Military and Aerospace Electronics. Today's event is sponsored by Elma Electronic in Fremont, California, Kontron in San Diego, and Behlman Electronics in Hauppauge, New York. This presentation centers on how updates to profiles in Sensor Open Systems Architecture, or SOSA, are increasing the adoption of the OpenVPX architecture. The OpenVPX architecture has evolved dramatically since its original inception, thanks in part to the Sensors Open Systems Architecture Consortium. SOSA is composed of members of industry and the tri-service branches, working together to create a common architecture for future defense systems. Our presenters today are Michael Monroe, Principal Backplane Architect at Elma, Mark Littlefield, Defense Vertical Product Manager at Kontron, and Jerry Hovdestead, Director of COTS Engineering at Behlman Electronics. This presentation is live and interactive, so you can submit questions at any time by clicking on the Ask a Question button in the presentation window. After our presenters finish, I'll open it up to questions from our online audience and for discussion among the panelists. First, a couple of housekeeping details. If you are running pop-up blocking software, such as the Google Toolbar, you will need to disable it to view this webcast. In addition, we recommend that you close down all other applications for better performance. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive. It will also be accessible from the home page at militaryaerospace.com. To get a copy of the PowerPoint presentations you'll see today, please reach out to the presenters. So, let's get started with Michael Monroe, Principal Backplane Architect at Elma. Michael?
Thanks, Jamie. In this episode, I will focus on the features of the SOSA architecture that are driving increased adoption of VPX systems by the defense agencies. To review, OpenVPX provides a descriptive nomenclature to define the different elements of a complete system. It defines these systems in terms of backplane profiles, slot profiles, and module profiles. VITA 46 covers many of the basic physical and electrical features core to the VPX architecture. In 2017, VITA 65 was broken into two separate documents. The primary document, VITA 65.0, has all of the basic definitions of existing backplane, slot, and module profiles. VITA 65.1 was developed to define all backplane, slot, and module dash numbers, as well as descriptions of specific VITA 66 and 67 modules. Backplane profiles are generally defined as a collection of slot profiles and the trace wiring between them. The backplane topology drawing seen here shows in general which slots are connected to each other and the size of those connecting pipes. It is important to note that the order of the planes illustrated in the topology drawing for each slot position does not represent the physical order of those connections in the slot profiles. For instance, the utility plane is always shown at the bottom, but is actually found at the very top of each slot. Each relevant topology drawing, as well as detailed information on port mappings and related rules and permissions, are found in the VITA 65.0 backplane profile chapters. The bandwidth and any special connector configurations for each backplane are found in VITA 65.1. One important change being driven by SOSA is the move to a 12-volt DC-centric power scheme. VPX backplanes will remain capable of distributing power across all three major power planes, VS1, VS2, and VS3, as well as being capable of supporting the three auxiliary voltages. However, to facilitate the reconfiguration of systems and simplify the provision of power, the only primary power planes that will be energized in SOSA systems will be those supplying the primary plus 12-volt DC power plane and the 3.3-volt DC auxiliary power plane used to power system management. VBAT will still supply 3-volt DC. This arrangement will still provide more power than can be cooled by conventional convection or conduction cooling. However, not having to consider 3 different primary voltages will make life simpler for system integrators. Some 3U module suppliers have already made this switch to exclusive 12-volt DC a few years ago, so we are confident that this will not present any major technical hurdle going forward. Each module profile has its own chapter in VITA 65.0. The primary slot profile to which they conform is identified, and any related rules and permissions are listed. Because each module profile may support different protocols, a dash number is defined for each unique configuration. These module profile dash numbers are listed as separate rows in its table in VITA 65.1. The relevant slot profile dash numbers are listed for each line in a module table. Slot profile definitions are one of the most evolved and complex aspects of the VPX standard. Each slot profile is defined in a separate chapter in VITA 65.0. The chapters for slot profiles are divided into sections based on the type of connectors used as well as the intended purpose of that slot profile. However, it's important to note that payload slot profiles may serve as data plane switches, and peripheral slot profiles may serve the function of a typical payload slot profile at any given backplane, and vice versa. Each slot profile is represented by a colorful figure such as the illustration on the right. This slot profile figure represents the makeup of that slot from top to bottom as physically arranged. At the top is the J0 utility section, which is always the same, although 6U cards VS2 is also assigned to the 12-volt power plane. Each connector within a slot profile is defined to support 1 or more channels of the defined planes. Each full connector segment can be divided into 16 wafers that each support a single bidirectional differential UTP link, ultra-thin pipe. Recently, wafers have been subdivided to support unidirectional differential links, such as for clocks or maintenance ports. Each colored section represents a different channel, and the color of that section indicates which plane those channels support. Areas without color were user-defined, meaning those areas of the slot could be used for undefined signals. The presence of user-defined areas has been recognized as the major cause of interoperability issues, and eliminating user-defined regions, thereby fully defining slot profiles, has been a major contribution by the Sosa effort to the VPX architecture. A slot profile name can be complex, but there are some basic aspects that can be quickly recognized. SLT indicates that it's a slot profile and not a module or backplane profile. 3 or 6 after the SLT indicates whether it is a 3U or 6U slot profile. Directly following the first 3 characters is sometimes a lowercase letter that identifies special clock support, such as radial clock support. When there is no such letter, the slot profile is supported by bus auxiliary and reference clocks. Slot type is given as a 3-letter abbreviation indicating the type of slot profile. Payload, switch, and switch slot profiles are the most common. The timing slot profile type is the newest type of slot profile and allows the support of radial clocks. Following the slot type is a long section of numbers and letter combinations that indicate the type of pipes or apertures and the numbers of each. As slot profiles have become more fully defined, this section of the slot profile name can become quite long and unwieldy. Another unfortunate aspect of this portion of the naming convention is that 2 different slot profiles may have the same type and number of pipes, but still be different because the sections, though in the same order, are located on different wafers. Apertures are probably the most important new feature of slot profiles and are enabling an explosion of new module capabilities. The dash number at the end of a slot profile allow for the definition of different connector loadings in the defined apertures. The 3 decimals identify a specific section in the VITA 65.0 document where the slot profile is defined in detail. And we use those 3 decimal numbers to talk about these slots because the names have grown so long. The dash numbers representing different defined connector loadings, if present, are listed in VITA 65.1. Within a VITA 65.0 slot profile section, following the colorful slot profile illustration, are two or more tables which name each signal position within each connector comprising the slot profile. Each row identifies the plane and the port that signal position is part. TX and RX signals are also identified. For instance, DPO1-TD is a data plane link number 1. An important aspect of these slot profile tables are the column names given at the top two rows. The top row gives the plug-in module column names from A to G, and the second row is the backplane column names from A to I. This is necessary because the plug-in module footprint is compressed and ground columns are combined. The chart border lines have been accented to help the reader see that there are only 7 signal positions for plug-in modules and 9 signal positions for backplanes. Despite this, be assured that both the backplane connector and the daughter card connector support all 9 columns at the mating interface. It's just the grounds of the daughter card footprint that have been reduced. Some of the signal names are DP for data plane port, which may be numbered from 0 to 3 if they represent a fat pipe. Transmit and receive are indicated in the naming as well as plus or minus. Another common signal name is CP-UTP, which is an ultra-thin pipe control plane signal. Again, TX and RX are identified as well as plus and minus. EP represents an expansion plane signal. Unless otherwise noted, the VPX convention is that signals on backplanes are wired from slot to slot as TX to RX and RX to TX. Plus is wired to plus and minus is wired to minus. A recent trend is the trend away from slot profiles with a lot of open user-defined areas and towards slot profiles that are fully defined. This will increase compatibility and help bring the Sosa slogan, one slot, many cards, to a reality. Notice that the 3 slot profiles on the left have a lower J2 section that is completely undefined as represented by the open white space. Even in the J1 region, there is some open space in each of the 4 profiles. The middle figure with all the extension lines is an example of the signal assignments as implemented by one manufacturer and is an example of how every possible signal position is actually used. Having undefined areas in a slot profile has made it difficult for system integrators to second source because backplanes end up being wired for one specific card. The 4 slot profiles on the right, however, are examples of where the industry is moving. This isn't expected to limit creativity. The cards that are designed for these new slots can have a lot of unique internal capability. This approach just requires that they assign common backplane signals in the same way. This collage indicates the new slot profiles developed within Sosa and proposed to the VITA 65 standards community. About half have already been adopted and can be found in VITA 67.0-2007. The others are in the process of being incorporated into the next release of VITA 65.0 and 65.1. The 4 sets of slot profile images are illustrated here. The slot profile illustrations are illustrated next to a photographic image of an actual backplane slot. This is just 3 examples. Working from left to right, the first pair of images shows a 14.8.7 slot profile which contains a half-size VITA 67.3D aperture. The photo shows a single MT optical module installed. The second and third pair of images are both for slot profiles containing VITA 67.3C apertures, which is the full-size cutout. In these 2 illustrations, the VITA 67.C replaces the J2 connector in a 3U slot profile. The 14.2.11 slot profile contains a full-size 67.3 aperture, which the photo shows to be populated by a combo connector module containing 4 SMPM coaxial contacts and a single MT optical ribbon ferrule. The 14.9.1 slot profile also contains a full-size 67.3C aperture. However, the photo shows that it is populated with a module containing 11 SMPM coaxial contacts arranged in 3 rows. The last pair of images is for a 14.8.8 slot profile, which contains a 67.3E aperture, which is also referred to as a full plus half because of the connector space it occupies. The photo also shows the aperture is populated with a module containing 12 SMPM coaxial contacts. It's important to remember that each slot profile aperture can support many different connector modules fitting that aperture size. Each connector module defines a different arrangement of contacts. There are three important apertures that support many new slot profiles. These new apertures support RF, optical, and apertures that combine RF and optical devices in a single aperture. These apertures are designed to utilize the full 1-inch slot pitch and are intended for fixed contacts that can be launched directly off the primary card PCB surface or off of a mezzanine. This means that the contacts in the backplane are sprung to accommodate movement to improve blind mating. VITA 66.5 makes use of the same apertures defined within VITA 67.3. The three apertures shown here are the half size, full size, and half plus full. Next to each slot profile icon, I've shown a few examples of modules that could fill that aperture. There is no end to the number and layout of connector modules that will be available. As new ones are developed, they'll be added to VITA 65.1, and the XY coordinates of the contacts for each new defined module are given. The 3U 12-slot CMOS backplane is shown here. 7 of the 12 slots contain VITA 67.3 apertures. These apertures are found in slots 2, 4, 5, 7, 8, 9, and 11. Slot 3 is a VITA 67.3 half-size apertures. Slots 4, 5, 7, 8, and 9 have full-size VITA 67.3C apertures, and slot 11 has a VITA 67.3E full plus half-size aperture. It's important to remember that each connector module shown could be replaced by the user with different connector modules of the same aperture size. Sosa, together with GTRI, currently have 4 new backplane profiles in development. 2 are power and ground only backplanes for laboratory developmental use. The other 2 are fully integrated backplanes, each implementing a different system strategy. They are expected to be very popular with system developers and will support interoperability demonstrations as they utilize most of the new Sosa-defined VPX slot profiles. Thank you very much for your time.
And thank you, Michael. Now let's turn it over to Mark Littlefield, Defense Vertical Product Manager at Kontron. Mark?
Hi, thanks, Jamie, and thank you everyone for attending. I hope you find this useful. Today I'm going to build a little bit on what Michael was talking about and kind of dig into why we defined the profiles that we defined and the organization of the profiles that are in the Sosa standard today and how they kind of map to real-world devices. So I'm going to start, though, by talking about what Sosa is trying to achieve. I'm not going to read the whole slide, but I'm going to read this first part, that the Sosa standard is basically a standard to capture business acquisition practices and a technical environment for sensor and C4 ISR payloads that foster innovation, industry engagement, competition, and allow for rapid fielding of cost-effective capabilities and mission platforms. Distilling that, basically what the government is trying to do by sponsoring this activity is to develop the VPX market so that it's easier to integrate systems and cheaper to integrate systems, and then easier and cheaper to upgrade those systems later on. So I cribbed this slide from a host presentation, and I hope the host folks don't mind, but this was such a great slide. Basically, you've got these platforms, whether they're aircraft or they're ground vehicles or naval vehicles, that are going to be out there for 25, 30, 35, 40 years or more. And you don't want to have to be tearing those airplanes apart or those vehicles apart to be able to upgrade a system. And today, that's what happens, is when you want to do a major upgrade, you have to pull the whole thing out, upgrade the backplane, upgrade the boards, everything, and then put the whole thing back in. And that's expensive, time-consuming, and you just don't want to do that very often. We want to be able to track the march of technology at the rate that the technology is marching. So, for instance, SBCs upgrade pretty frequently. So you want to try to upgrade those pretty frequently. Other devices, like maybe an I/O device, wouldn't upgrade quite so frequently, and so you want to have that flexibility of changing at the rate that technology is driving the change. So Sosa is already, it's only been in development for a couple of years now, but it's already starting to drive that change. In the past, we had vendor-specific pin assignments on boards. We did have VITA 65, which I was very happy to have participated in its early incarnations, but 65 is proving to be a little too flexible for trying to drive the change that SOSA is trying to change. But in the past, we had vendor-specified pin assignments, backplane incompatibility between generations of hardware, and really not a lot of rules with regards to board-to-board connectivity. It was kind of the Wild West, if you will. What SOSA is trying to do, and what SOSA is in fact doing, is to create common slot and module profiles that have no user-defined pins. Michael said that. There are two exceptions, and I'll talk about why those exceptions exist. But basically, the user-defined pins tend to kill interoperability and kill upgradability. And then to define clear backplane implementation rules and guidelines that designed to enable vendor-agnostic connectivity and future board-level upgrades and updates. We're not defining physical backplane architectures. They all shall have this many slots connected in this way, but rather defining the rules by which the slots can be connected, and what signals are allowed to go between slots and what signals go to the outside world and what have you. So what I'll do is I'll start with the 3U profiles because they're a little more complex than the 6U, and then you'll see how the 6U kind of fell out of the 3Us. So we have switch profiles, we have functional module profiles, and we also have radial clock profiles, but I'm not going to be talking about the radial clocks because they're pretty specialized. So I'm going to focus on the switches and the functional modules. Looking at the switches, because they're probably the easier portion of it, we have two profiles, a primary and a secondary. And I should also mention that the SOSA also has legacy profiles, and I'm not going to talk about the legacy profiles here. The legacy profiles are basically there to allow systems to kind of bridge the pre-SOSA and post-SOSA worlds, but there's language regarding how they're implemented and so on. And you can also always read the snapshot to see more about these legacy profiles. So in the switch profiles, it's pretty simple. There's a primary and a secondary profile. They basically are there whether or not you have the need for optical connectivity or not, and so it's pretty straightforward. Insofar as module profiles go, they both are 40 gig Ethernet data plane, 10 gig Ethernet control plane, and whether or not they have the aperture. So in processor and I/O slots, again, it's a little more complex than the switches, and we weren't really able to narrow down to like a single profile. That was the real goal, was to have a single profile, and it really couldn't be done because in 3U there's just not enough pins to be successful in doing that. So what we did is we have two primary profiles and one secondary. The primary profiles, generally called the I/O intensive, the two primary profiles are the I/O intensive profile and then what's called the compute or RF intensive profile, and that's sometimes called in the literature the payload slot profile. So looking first at the intensive slot, I/O intensive slot profile, this is basically a general purpose SBC. It has your basic communication planes, your data plane, your expansion plane, your control plane, but it also has things like video, USB, storage, serial ports, GPIO, as well as the XMC mapping. So you have the ability to add customization through putting on an XMC and then mapping it to the backplane. But in the module profiles, in addition to those primary communication planes, the data plane, communication plane, and expansion plane being defined, you also have the video defined, you have the USB defined, you have the storage protocols defined, you have the GPIOs, the actual the signaling behaviors of the GPIOs and voltage levels defined. So you can really have a good expectation that you can, pick from a number of vendors and expect those boards to all work together, and likewise go from one generation to the next, and again expect things to simply work. Looking at the RF or compute-intensive slot profile, this is the real workhorse. This is what we expect most people to design to, whether it's a processor or an I/O board or storage board or what have you. Its focus really is on those primary communications planes: the data plane, control plane, and the expansion plane. That you notice there's no kind of you might call it commodity I/O type on here. There's no USB. There's no serial ports, with the exception of the maintenance port, and those maintenance ports are a little special types of ports intended just for maintenance of the board. And if you want to learn more, I'd recommend taking a look at the Sosa snapshot for details on that. But again, this is really the workhorse for high performance computing, for receivers, for I/O boards, and so on. Again, it's based on 40 gig Ethernet data plane, 10 gig Ethernet control plane, and PCIe Gen 3 expansion plane, but it also has accommodations for Aurora, because FPGA to FPGA communication is also pretty important for these kinds of systems. So let's use this and take a look at some examples. So high performance SBC. You have a big number crunching engine with big pipes to feed it. This is pretty straightforward. Focuses on streaming of data. The data sources could be data sources or drains, rather, could be the primary data plane, the expansion plane, or even like optical or RF connectivity. And you then have the control plane for system control messages, so that you've got basically out-of-band communications paths. That way you're not interfering with data streams by inserting command packets. Another example is like a high-performance receiver, something for converting and processing analog signals. You basically, in this model, would be bringing data in through your RF connectors, through the aperture that you find there at the bottom of the profile. You do whatever early stage of processing you would do on the board, and then your outputs could be perhaps the expansion plane via PCI Express, or maybe Aurora if you're passing data to other FPGAs. Or it could be out the data plane and passing out to the rest of the multi-computer. And again, you've got the opportunity for a control plane for that out-of-band system control messages. But you see, it's the same slot profile as the high-performance computing example. Another example would be a GPU for high-performance computing. Again, the same profile. In this case, I've introduced the secondary profile that expands the expansion plane, because you might have a case where GPU can make use of those extra lanes of PCI Express to improve the system performance. Basically, though, GPUs generally don't have Ethernet or serial ports, so the control planes and maintenance ports, excuse me, wouldn't be used in that case. Although, looking forward, we're starting to see, these system on chips where you've got a big GPU with perhaps a few cores of ARM or something like that, or an Intel core on there to work together. And so you might want to make use of the serial ports or the Ethernet ports and so on. But if you don't have them, that's okay. You still can use the same slot profile. That gives you 8 or 16 lanes of PCI Express that form the control and data path, if you don't have the Ethernet or the serial ports to provide those capabilities. And that essentially, in this case, what you're doing is the GPU is essentially a peripheral to a host module that you'd be connecting up either directly or through a switch. Another example is storage. Again, the same profiles, but if we look at kind of storage models going forward, network attached storage or NVMe are going to be the most likely storage modules that we'll see in these kinds of systems. And both of them fit this profile, these profiles very well. With network attached storage, you would most likely use the data plane to maximize your performance, your gazinas and gazautas. and then you have the ability to have the control plane or maintenance ports for maintenance or control messages. For NVMe, most likely, and well, I think by definition, you'd be using the PCI Express ports. And again, in that case, probably the control plane and maintenance ports would be unused, but it all depends on the design of the board. The last example is the FPGA board, and the FPGAs are both a blessing and a curse because they're so flexible, but that flexibility brings complications. It's hard to generalize FPGA boards because they vary in features and performance. They may or may not have onboard processors, so you may or may not have Ethernet or for data plane connectivity or control plane connectivity. You may or may not have serial ports for the maintenance ports. So it's really depending on what the application and what the developer of the board really wants to do. But the expansion plane is really critical for FPGA-based computing boards. It could, in fact, be the primary data path for the board, and you want to use those for FPGA to FPGA links. FPGAs are tending to really push the limits as far as throughputs on these systems go, and so again, I guess what I'm stressing here is that the same slot profiles can be used in all of these different types of boards. So the one exception to the rule of no user I/O, user-defined I/O, is this profile, 14.2.3. And you notice in this case, it's virtually all user-defined. So one of the rules in Sosa is user-defined I/O cannot go between slots. It has to go to the outside world, and that's really what this profile is to do. If you need to have specialized either lots of GPIO for hooking up to like legacy aircraft systems or something like that, or very specialized I/O, like maybe you want to bring in some legacy I/O that's not captured by the standard, this would be the way that you would do it. This basically allows you to aggregate those signals, and then you have the expansion planes or the control planes to be able to move those signals around within the system. It can be implemented as an intelligent device, which you would then probably use the control plane as the control and data path, or a non-intelligent device in which you would use the expansion plane. So switching gears to 6U, we have 3 primary slot profiles and 1 secondary. You'll see in a moment, and again, I'm not going to talk about the radio clocks. There's radio clock profiles in the standard. But you can see where we've basically leveraged the 3U to define these 6Us. With a lot more signals, a lot more pins to play with, 6U is a little bit easier. It gives us kind of ultimate flexibility. The primary 6U slot profile is this one. If you look at it, it's kind of a mix of the I/O intensive and the compute intensive slot profiles, in which we have big fat data pipes coming in and out of this board. We have big fat expansion plane to play with. We have 2 apertures for either optical or RF. Plus we have all of the kind of commodity, if you will, I/O, plus the XMC mappings. So this is really the most general purpose slot profile, and all of the signals of 6U give us that flexibility. The secondary slot profile is virtually the same, but it basically swaps that XMC mapping for yet more expansion plane. And this was driven by the need largely of like FPGA boards to be able to give you a lot more FPGA lanes or a lot more serial lanes in between FPGAs to play with, but also like high performance peripheral devices can make use of those extra planes as well. And then one thing I didn't mention was I'm going to jump back for just a moment. Again, the user I/O slot profile, that one's got the same basic rules as the 3U, where it's all intended for out-of-box communication, and you've got the expansion plane or control planes for control and data movement. So just to give you a couple of concrete examples, Kontron recently announced, and we're shipping today, both an IO-intensive SBC and a compute-intensive SBC built against these profiles, and designed in alignment with the snapshot 2 of the SOSA technical standard. The VX305C 40G and 305H 40G, and I just bring these up as an example of how you can leverage these profiles to make real world hardware, and we're shipping these today. So in conclusion, SOSA is really driving future VPX architectures, and it's early days for SOSA. It's still an evolving standard. We kind of jumped out ahead and built boards against the standard because we thought it was stable enough to be able to build basic general purpose SBCs to meet the standard and we wanted to kind of help seed the market with early product. But SOSA is really addressing the problems that we've seen in the last years of problems with vendor interoperability, problems with future upgrades and updates, problems of vendor lock, both at the module level, at the slot level, and at the system level. And it provides truly standard building blocks while giving suppliers room to innovate within their product space. It eases system integration issues. We want to really make it much easier for our system integration partners to build system using these components. And then the final goal is we really want to be able to bring faster upgrades to the warfighter and be able to allow the warfighter to leverage the march of technology. And so that's why we're working so hard on this standard, and why at Kontron we believe this, and we're supporting this. So thank you very much for your time.
And thank you, Mark. Our final speaker today is Jerry Hovdestad, Director of COTS Engineering at Behlman Electronics. Jerry?
Yeah, thank you, Jamie. And I'm here just to talk about power now, to support some of the things you've heard about, all of these backplanes and profiles and what's happening with the power supply. The VPX power supply has been around for about 8 years, and Behlman has been involved for that period of time. In the past, we had 3U power supplies that could deliver about 500 watts. Each 3U power supply had 6 outputs: 12 volts, 5 volts, 3.3, an auxiliary 3.3, and an auxiliary plus or minus 12 volts. We also had 5 user-defined pins. There was an optional capability of intelligence, no provision for 3-phase inputs, which we're seeing now. There are lots of systems that have 3-phase AC, and that needs to be taken care of. There was no clear definition of energy storage and how to do it. Energy storage has been a requirement for power, and in most systems in the past, you had to hold up while power was being switched. And although the specification addressed it and mentioned it, there was no clear way of building it, of hooking it up, of defining input and output or capability for it. Also, there were certain functions in the specification that weren't clearly defined, such as NVMRO or system reset. There were options, and there's a number of different ways of doing it, and all of these variables are get in the way of system interoperability. So, wrong way. And in the 6Us, things were similar. Again, we get around 1,000 watts on a 6U power supply, 5 outputs. There was no 3.3, just the 3.3 aux voltage. The one thing we had in the 6U world was there was always what's being envisioned for SOSA. There's always been a 12-volt centric 6U definition, and we have been shipping many systems for many years that are 12 volt only, with a 12 volt output and a 3.3 aux. So that has existed in the 6U world, and in the 3U world, that's being added to the VPX specifications because it doesn't exist At the moment, there's only provision for 6 outputs. On the 6U card, you had 7 user-defined pins. Again, user-defined pins give you or get in the way of interchangeability, interoperability. Every manufacturer takes the pin and does something else with it, and you can't interchange cards. It gets in the way of the interchangeability, the upgradability. That's the goal of Sosa supplies and Sosa systems. Again, no clear definition of energy storage in 6U, and functions also need definition. I'm going to get going in the right direction one of these days. Okay, 3U and 6U in the present. What we've seen in the present is that over the past 8 years, we've seen power increasing, whereas power was around 500 watts in the early days or less for 3U. And 1,000 watts. 6U has stayed around 1,000 watts. We've seen some modest increases in 6U power, and 3U power has gone up. You see 700, 800 watt 3U supplies available these days. There still has been no change in user-defined pins, intelligence definition, energy storage, or functional clarity. So right now there's a working group in trying to change the specification to clarify all the issues that get in the way of interoperability, and Sosa is looking for that type of power supply to use that in the future. Sosa supplies now, they're trying to maximize the amount of power available. So to simplify it also, they're going to 12 volt only, which instead of having to worry about how much 5 volt power you have, how much 12 volt power, how much 3.3 volt power, you only have 12 volts, you only have a maximum power. It greatly simplifies the interchangeability of power supplies. We're trying to eliminate user-defined pins. And there are some functions that we found may be necessary, and we probably will be assigning the user-defined pins to those functions, such as 3.3 sensing and sharing. The 3.3 aux has no ability to, no share pins, no sense pins, but the power level on the 3.3 aux, it's only 3.3 volts, and you need to have some sort of a share control or sense control to basically keep it at acceptable levels throughout a system as the power increases on these voltages. The intelligence, there's committees working right now to basically firm up the intelligence for power supplies. The basic functions, everybody would like to be able to read power supply input power, input current, input voltage, output power, output voltage, currents, temperatures, and various functions in the power supply. There's a lot of information you can get from a power supply that is very useful to a system. If you know your input power, you know what your system is doing, you know what the system, how it's supposed to perform. Changes in input power can give you a key to something might be going wrong. You can look at your output power and maybe see exactly what might be going on, give you an advance warning of problems that might be occurring. So intelligent power supplies are the wave of the future, and the commands, the definition of the intelligence, the software function needs to be standardized so that everyone doesn't have a completely different software program or a different means of addressing the power supply to handle that. We're trying to enhance the interoperability and the standardization of power supplies, make it much, much easier to upgrade, much, much easier to use the supplies and interchange supplies. So again, we're trying to maximize vendor interoperability and maximize future upgradability. For example, if a system can handle increased power, needs increased power, you should be able to just plug in a higher power supply, provided everything, all the other factors are taken into consideration when you increase power. Okay, in process right now, of course, the spec is being changed to add a 12-volt centric configuration for 3U. They were clarifying and better defining the energy storage configurations. There are a number of different existing ways of doing energy storage, and profiles need to be assigned to those different capabilities to allow backplane designers to be able to configure their backplanes to handle these various different types of energy storage that are available. System management capabilities and commands are attempts being made to standardize those, so that when you ask for 12-volt voltage and 12-volt current, you're going to get it. You're going to get the same thing we're using the same command, no matter what supply you are using, no matter whose supply you're using. Again, these things do need to be standardized. There's a little bit of ambiguity right now in the standard as the way it exists, and work is underway to standardize the software and the hardware to make it much more interchangeable and upgradable. The intelligent power supply that I mentioned, the functions that are being addressed, the functions you can get right now from a lot of manufacturers is you can read voltages and currents and temperatures. You can also get inventory information, manufacturers, part numbers, serial numbers. You can read from the power supplies, but the same software with one manufacturer won't work with another manufacturer, so that needs to be standardized. In addition to the column on the left, there is also the industry is looking for fault logging for help in troubleshooting, time totalization, counting, so you know when a fault may have occurred, output sequence, the ability to sequence outputs, the ability to, if that's necessary, you want the ability to be able to turn off or on individual outputs to sequence them, turn one on before the other. Fault detection thresholds. One system, your fault level might be different than another system, so it would be nice to have the ability to adjust those thresholds on a system-by-system basis. System reset is a function that's in the specification now, but it's not very well defined, and the work is being done to standardize on the system reset function. And the energy storage element, the smart power supply can also report on the energy storage. You want to be able to know if your energy storage is functioning, and if it is, if it's ready, and if there's a problem with the energy storage, it basically can fault isolate any problems with energy storage. Work being done right now on the specifications is in original VITA 62, now VITA 62.0. There's a working group right now in progress that is upgrading VITA 62 to add some of the features that I've mentioned. There's a VITA 62.1, which is almost, I believe, ready to release, which will define a three-phase front-end card for VPX applications. So it'll give you the ability in 3U systems to handle three-phase 400 hertz inputs and provide a standardized output that you could interchange system vendor to vendor, system to system. Basically, it defines a front-end card for three-phase inputs. And there's work being done for 270-volt DC inputs and VITA 62.1. There's also other specifications to handle 270-volt DC inputs. But these are the work that's ongoing right now to upgrade the power supply specifications. Behlman, it's just a picture of Behlman. On the right, the existing 6U 12-volt centric cards that we've been building for years, and on the right, a model you can probably get about 800 watts fairly conveniently on a 12-volt only 3U card and a 12-volt centric card. So These are our Sosa model numbers for 3U and 6U standard cards. There are always problems as you push power where your system needs to be able to handle the power, handle the cooling, handle the increased capability. But that work is ongoing to take care of that so you can actually maximize your power usage in your systems. And lastly, there's a three-phase input module for VPX. And it's been around for a number of years, and now work is being done within the standard to basically define the three-phase 3U AC input card. And that's the last of the slides.
All right. Thank you, Jerry. Now it's time to take questions from our online audience. You can submit questions at any time by clicking on the Ask a Question button in the presentation below. And I will get started shortly. Okay, Michael, what is the maximum number of fibers that can be accommodated in a VITA 67.3D half-size module?
Jamie, a half-size module can support up to 2 MT ferrules. Each MT ferrule can hold either 12 or 24 optical fibers in a ribbon. So that means a half-size module can currently support up to 48 optical signals. However, there have been new MT ferrules developed within the ground-based telecom field that use lenses for the interface. This reduces the amount of force needed to hold them together, and it also increases their immunity to debris because they're not as likely to damage themselves when they're closed on debris. And these MT ferrules can hold 4 rows of 16 fibers in the same space, same housing. We've used them in our MT ferrule modules for a total of up to 128 fibers in a single half-size module. So the future is looking pretty bright for optics.
Okay. And Mark, what is the difference between a primary and secondary profile?
So both are completely free to be used by the standard, but we use the definition of primary and secondary to say, to sort of promote the maximum commonality that we can promote. So, for instance, I guess the best way to describe it is, if you can solve your problem with the primary profile, you should use the primary profile, and only use the secondary profile if you require those specific features that the secondary profile brings. But both of them are permitted within the standard.
All right, thanks. Jerry, what does NVMRO mean?
Okay, yeah, thanks, Jamie. NVMRO is a non-volatile memory read-only. It's a signal that is defined for the power supply. It's defined for the whole system. It's a line that is used to lock down memory in the system, so it can't be changed. It's not susceptible to viruses. It's important in power supplies because it needs to work in conjunction with system management power, so we do need to be careful, and we do need to carefully define how NVMRO works in conjunction with system management power.
Thank you. Michael, are MT ferrules available for single mode as well as multi-mode fibers?
Yes, they are. And that is defined in the section of VITA 65.0 for optical MT ferrules, but you can use single or multi-mode fibers.
Okay. Mark, for IO-intensive profile, do all items identified have to be populated, or can a board be SOSA compliant if, say, all wafers are accurate, but the video is no connect?
That's a great question, and the problem is it's a little bit complicated. profiles will be allowed to be depopulated, and there'll be specific rules to define. In fact, I think already in Snapshot 2, there are specific rules to define how ports can be depopulated. But we're actually working on that text right now. So I would say take a look at Snapshot 3 when it becomes available in a couple of months for all of the details. But the short answer is yes, you're allowed to depopulate ports, but only with specific rules and in specific orders.
Thank you. Jerry, how is keying being revised?
Okay, because we're adding different configurations to VITA 62, we need to revise the keying to make sure that you can't plug in one module that's incompatible with another module and blow up your system. So we're looking carefully at all the new functions and addressing the keys to make sure that this doesn't happen. That work is being in process in conjunction with the Sosa upgrades to the VITA specifications.
Thank you. Michael, what is the maximum number of SMPS or nano RF contacts possible in a full-size VITA 67.3C module?
Okay, Jimmy. So the up to now in defined slot profiles, we've primarily seen the SMPM contacts, but much smaller the SMPS or the nano RF contacts. There are modules out available now that support 16 nano RF in a single full-size VITA 67.3 module, but they are working on a module that will hold 24 nano RF or 24 SMPS modules. There's similar sizes, slightly different and intermating, but because you can change modules on a backplane, the user can very easily. It's a nice upgrade path.
And thank you. Mark, how does Sosa relate to VITA 65? Does it replace it?
That's a great question. It's actually a question I get asked a lot when I talk with people about Sosa. The hardware working group of Sosa is working very closely with VITA 65 to make sure that anything that we might come up with that's new gets rolled into VITA 65. So everything that's going to be in Sosa, as far as profiles and the things that are appropriate for VITA 65, will be moved into 65. And in fact, there's actually opportunity for the greater community to discuss anything that's proposed from Sosa. And so you actually have the means to kind of feed back into the standards activity. What you'll find, though, that Sosa will be more restrictive than VITA 65 is with regards to things like connectivity or as I mentioned earlier, about depopulating ports and things like that. So I would say VITA 65, what's in Sosa will be reflected in 65, but Sosa will be more restrictive than what 65 generally will allow.
Okay, going to bounce back to Mark. Got a follow-up question. Do all signals stated in the SLT profile have to be present, or can you no-connect the pinouts to be compliant to the spec?
Yeah, again, it depends on the exact signal. It's really best to just review the rules within the snapshots to see, what signals can be completely disconnected and which cannot, and which can be, say, depopulated. So, for instance, you might have, 8 lanes of PCI Express, but you're allowed to depopulate those down to 4 lanes, or even 2 lanes, or even 1 lane, but you have to do it in a particular order. And so it really depends on the port, and it depends on again, those rules of depopulation.
Thank you. Jerry, are these actual vehicles and aircraft that use VPX?
It's really hard to tell. Within Sosa and in VPX, it's been around for many years, and there are small quantities of systems out there actually flying or around. There's some programs where there are hundreds of them out there, and there's some that are, just limited numbers, and it's really hard to tell exactly what the the VPX systems are actually on right now. However, we do know because of the joint memo that is being planned for use on just about everything. In fact, everyone has to show or justify if you're not using an open system like Sosa. They have to justify why not. So everyone, for all future programs, should be using the something like the Sosa, the Sosa specifications.
Thank you.
I'd just like to add in that
Sure.
both the Air Force and the Army have done demonstrations on early Sosa systems utilizing that CMOS backplane. The Air Force has flown systems in an Agile pod, I don't know on what type of aircraft, and the Army has demonstrated the CMOS backplane system in a Stryker ground vehicle. There may be other tests that have been done, but those are just two that I'm aware of.
Thank you very much. And Michael, with the new 12-volt centric Sosa power scheme, what is the maximum amount of power you can bring onto a 3U card?
274 watts, and that would be a challenge to any company to cool. Luckily, we have the liquid flow-through cooling scheme that Elma's just demonstrated and was developed within the VITA community, but that's a lot of power on a 3U card.
All right. I'm going to say, on behalf of Military and Aerospace Electronics and Endeavor Business Media, I would like to thank Michael Monroe, Principal Backplane Architect at Elma, Mark Littlefield, Defense Vertical Product Manager at Kontron, and Jerry Hovdestead, Director of COTS Engineering at Behlman Electronics. This presentation will be archived within 24 hours and can be accessed from the Military and Aerospace Electronics homepage at www.militaryaerospace.com. A reminder email message for the archive will be sent to registrants with a link to the archive. We thank you for joining us today. I'm Jamie Whitney, Associate Editor of Military and Aerospace Electronics.